Alright, so here are the questions that are out of 2.5. I think there are 16. Let me see. I think there are 16 problems. 4, 8, 10, 12, 14, 16 problems. So these are the problems that are similar to the questions on the WebAssign homework. There was one that was not included in the book, so I just took the actual question 3 on WebAssign, and included it in the list of similar questions for WebAssign. Alright, so let's look at these. First one says, if f is continuous on all real numbers, what can you say about its graph? Well, it has no holes, it has no jumps, it has no vertical asymptote. Question 3. From the given graph of f, state the numbers at which f is discontinuous and explain why. Well, anywhere where you have to lift up your pencil or pen, it's discontinuous, so you get discontinuity at -4, -2, +2, and +4. So it's discontinuous at -4 because it's not defined at -4. It's discontinuous at -2 because it's the left and right hand limits do not agree. But you can also say that it has continuity from the left. It's discontinuous at 2 for the same reason the left and right hand limit do not agree, but you can also say that it is continuous from the right. You can also say at 4 it is discontinuous because the left and right hand limits do not agree, but you can also say it is continuous as you approach 4 from the right. Now they say determine whether it's continuous from the right, left, or neither, and I just went over that, but you can see it there as well. Now they say state the intervals on which it is continuous. Well, if you have a solid dot at any one of these endpoints, you want to include that. So you're talking about bracket -4 to parentheses -2, parentheses -2 to parentheses +2, and then bracket 2 to parentheses 4, and then parentheses 4 to parentheses 6, and then finally parentheses 6 to parentheses 8. Now they ask you to come up with a graph that is discontinuous at 0 and 3, but it's continuous from the right at 0, and it's continuous from the left at 3. So if you have discontinuity, you expect to have some sort of break there. And it's continuous from the right at 0, so you would define it right there at, as x approaches 0. And this one from the left at 3, so you'd put a solid dot there as it approaches at 3, so it has continuity from the left. They talk about a toll road. The toll road is $5 except between 7 and 10 and 4 and 7 p.m. where the toll is $7. So if you take a 24-hour period from 0 to 7, it is 5, and then from 7 to 10 it's 7, and from 10 to 1600 hours, which is 4 p.m., it's 5, jumps up to 7 and back down to 5 again. So it has discontinuity at those 4 numbers. What is the significance of that? Well, the driver will have to pay $2 more because of a higher toll. Alright, now in this one they ask you to explain why it's continuous or discontinuous. First one, the temperature at a specific location as a function of time. Well, no matter what the temperature is, say at noon, as your clock winds down to 1 o'clock in the afternoon, the temperature is going to change. Whether it goes up or down, it's going to be gradual and smooth, so it is continuous. The temperature at a specific time as a function of the distance due west from New York City. So as you go west from New York City, the temperature will change, and it's not going to be a sudden change. It will be gradual and smooth, so that is continuous. The altitude above sea level is a function of the distance due west of New York City. Well, at that point, you have discontinuity, and in very rare cases, but if there's some sort of a cliff, you would have immediate jumping to a different value. So because there are cliffs somewhere in the U.S. west of New York City, you would have to say this function is discontinuous. The cost of a taxi ride as a function of distance traveled. Well, if you ever take a taxi, the meter ticks up a certain amount, small increments of $1 as you go along, and so those jumps from one price to another make it discontinuous. The current in a circuit is either 0 or 1, so that is by definition discontinuous. Now here's a weird one. They tell you g of 2 is 6. And they say find f of 2. And they give you this limit here equals 36. So you start out with the limit equals 36, which means 3 times the limit of f plus the limit of f times the limit of g equals 36. And we know the limit of f, or we don't know the limit of f, but we know it's f of 2 because it's continuous. And the limit of f is f of 2, the limit of g is g of 2. And now we know g of 2 is 6, so put a 6 in there. So this is 3 times f of 2, and this is 6 times f of 2. When you add them together, you get 9 of them, 9 of the f of 2's. And that equals 36, so simply divide by 9, and you now know that f of 2 has to equal 4. 21, they ask you to, I think they ask you to check continuity at the value for a. So if you look at the graph, you're expecting it's to be discontinuous, but let's talk about it. As you approach minus 11 from the left, you're going to be using x plus 3. And you can do direct substitution and you get an answer of 2. If you approach negative 1 from the right, you're going to be using 2 to the x. And again, that's an exponential function. You can plug in directly and you get 1/2. Now since the left and right hand limits are not equal, we can say the limit does not exist at minus 1, and it is discontinuous at minus 1. Now explain why the function is continuous for every number in its domain and state the domain. Well, it's a rational function of polynomials, both of which are continuous on their domains. Polynomials are defined everywhere, but the rational function is defined only places where the denominator does not equal 0. And if you factor that, you'll find that when x equals negative, or when v equals negative 5 or positive 3, you're dividing by 0. So it's defined everywhere on its domain, which is everything except for 3 and minus 5. Locate the discontinuity and illustrate it by graphing. So if you look at the graph, you're going to see 5 pi over 2, pi over 2, negative 3 pi over 2, so on. So where is it discontinuous? Well, it's where 1 minus sine of x equals 0. That's definitely where it's discontinuous. So one of the things you might say to yourself, well, what about if this guy is negative? Well, it technically never gets to negative because sine goes from minus 1 to 1. And if this is minus 1, that's 1 minus minus 1, which is positive 2. And if sine is positive 1, 1 minus 1 is 0. That's a problem. And so where does, you don't have to worry about this thing being negative. You have to worry about whether it's 0. And we look at where it equals 0. And we get sine of x equals 1. And where is that? At all these values of pi over 2, and then add 2 pi or subtract 2 pi to get the other values where it is discontinuous. Alright, 37. We worry about its domain, so you set this guy to be greater than 0 because natural log only accepts numbers greater than 0. So, how do we find out where this guy is greater than 0? Well, with linear inequalities, the way you do that is you find out where the numerator equals 0, where the denominator equals 0. And I factored that and set each one equal to 0, solved for that. And I got these three values, minus 1, 5, root 5, and negative root 5. And you divide up your number line into, with those three numbers, gives you 4 regions. And now you check a test value in each region with the original inequality. Okay, so root 5 is a little bit greater than 2, so you might want to try 3. Plug 3 in here, you get negative on the top and positive on the bottom. Negative over positive is negative. If you plug in 0 here, you get positive 5, which is positive. If you plug in negative 2, you get positive over negative, which is negative. And if you plug in negative 3, you get negative over negative, which is positive. Now we want greater than 0, so we're going to take this region here and that region there. So your domain is from minus infinity to minus root 5, and also from minus 1 to positive root 5. So now they ask us to take the limit as x approaches 1. Well, we have to be concerned if 1 is in our domain. Is it? Yeah, it's inside that interval there, so we can take the limit and do a direct substitution because this is a combination of a logarithmic function and a rational function, and it's a composite of those, so we can do it. And we do direct substitution and we get ln of 2, which also happens to equal f of 1. 36 is a bit tricky because you're taking the limit of a composite function, so sine of tangent of cosine. Well, cosine is has a domain of minus infinity to infinity. Okay, and the range of cosine is minus 1 to 1, and that becomes the domain of the next function, tangent. And the domain of tangent includes those numbers. That's not a problem. And when you plug those numbers into tangent, you get anything from minus infinity to infinity. And that range for tangent becomes the domain for sine, which it is. Sine's domain is everything. So the domain of f equals sine. So this guy is okay basically because we've shown that the domain of one becomes the range of the other, becomes the domain of one, becomes the range of the other, becomes the domain of the other. So it is a composite function and it's continuous over its domain, which is everything. Now if we plug in pi over 2, which is what we're approaching for our limit, we get cosine of pi over 2 is 0, tangent of 0 is 0, and sine of 0 is 0. So this limit approaches 0. Alright, this function is a continuous function throughout its domain because it's a composite of an exponential and a polynomial function and a root function. So its domain is everywhere where this guy is greater than or equal to 0. Now where is that? Well, you got to find out places where this equals 0 and divide up your number line like we did earlier. If you plug in 1, negative 2, negative 4 for your a, b, and c, you get 1 plus or minus root 5. So divide up your number line with those two numbers. Check a test value in this guy here, and you write down plus or minus in each region. And we only want places where it equals 0 or is greater than 0. So we include this first and third regions with the endpoints as well. So now we ask is 4 okay? Because that's what the limit we're taking is. So 4 is okay. It's in this interval here. So we can just do direct substitution and we get our answer is 9. On this one, it's continuous on the interval minus infinity to minus 1, between minus 1 and 1, and greater than 1 to infinity. The only problem that you want to check is where is it continuous at these points in between, at minus 1 and positive 1. So if you look at it from the left and the right, from the left and right they're different, so it's discontinuous at that number. From the left and right they're the same, and at the point it equals the same value, so it is continuous at positive 1. And the same thing idea here, it's continuous for minus infinity to 1, from 1 to 4, and 4 to infinity, all open intervals. But you have to worry about it at 1 and at 4, so you're going to have to take the limit from the left and right and look at the point. From the left you get 2, from the right you get 2, and at the point you get 2, so it is continuous at 1. From the left and the right you get two different values, so it's discontinuous at 4. And f of 4 equals minus 1. Now if you approach from the left and you get minus 1, and at the point you get minus 1, that means it has continuity from the left at 4. Okay, and the last one, same idea. 3 intervals that are open, and then you worry about the points in between at 0 and 1. You look at from the left and the right, left and the right. From the left it's 2, from the right it's 1, so it's discontinuous at 0. But because from the right it's 1 and at the point it's 1, it's continuous from the right. This one from the left is e, from the right is 1, so it's discontinuous at 1. But f of 1 equals e, so from the left is e and at the point is e, so it's continuous at 1.